good for coral reef building. And so look here, there's a big disaster. These were calcite corals. Those are rugose and tabulate corals. They're not related very close at all to the scleractinians. And after this disaster, it was in Aragonite Sea, so the corals originated here as aragonite. And so they have these peaks, but right about here, the ocean started moving again, and so no more reefs, or there were reefs, but they were pitted. And then here, the reefs started up again. And so that's why we have good reefs now, is because our continents aren't moving and taking up that easy. This is just the same picture again, but it's just showing there's different, these are scleractinian corals, or these are scleractinians, and they're still living and making coral, but they're not making reefs very well, they're petering off. But here are the rudis. Those are bivalves that make calcite. And so they were making what you might call the reefs. Now they are not exactly reefs but there's still lots of calcium carbonate and structural. And this is why, one of the reasons why the diversity of corals is great, even though there's no reefs, is these bivalves are their reefs. Oh, here's pictures of what they look like in life. And here is the coral, and here's the bivalve, the rudis. And in very sedimentary areas, it's just rudis. And on wave action areas, you get small, tiny reefs of corals when it's too much wave action for the rudis. But most of it, the corals were using the rudis as reefs. In other words, corals don't make the reefs. The bivalves make the reefs, and the corals live on them. And what's speculating that's kind of interesting is the corals are kind of taking over the niche of coral and algae, because on big wave action areas in the surf, you get coral and algae kind of making a small piddling reef, but it's still coral and algal reef. And then in these areas, they're binding the root gosets together, like coral and algae can help bind coral. Here's the picture of the marine lab out here in Pago Bay, and here's a ridge or a reef made of coral and algae. And so that's what the corals were doing back then. One thing that's a side point is when we had the great Cretaceous extinction, we had two things going at the same time. We had this big bolide or meteor or asteroid hitting the Earth and making a tremendous amount of sediment in the air. At the same time, or over a longer period, you had a huge volcano called the maker of the Deccan Traps in India. It was about a third of the area of India, and it was 6,000 feet of lava, 2,000 meters of lava. Here's what's left of it now after 65,000 years. That must have been an awful lot of CO2, is that asteroid and the Deccan Traps, but the corals didn't do bad. That killed all the dinosaurs, all the ammonites, all those bivalves we saw, but the corals aren't officially even a mass mortality of corals. Well, my speculation on that is that the temperature of the ocean has a cap, and it already had 70 million years of warm air. So when this bolide hit, it really changed everything for many animals. But for corals, it's already reached as hot as that water is going to get and as low as the pH is going to get. So these things really didn't seem to have much effect on corals. And here's a history of corals I think is very interesting. The Triassic mass extinction was terrible for corals. For marine life in general, on that Triassic-Jurassic mass extinction, that had about 53% survived, which is pretty bad. It killed about half of them, but it killed 3/4 of the coral. But then the Cretaceous Paleogene mass extinction, that's the one where the bolide hit and you had the Deccan Traps volcanoes. About 53% of marine life were also killed again. But instead of 3/4 killed, only about a third of the genera went away. That doesn't even count as a mass extinction. And what's most important to that is that, remember when you had that sudden big reef building in the Jurassic and you had 100 new genera of coral coming up in a few million years? Those there's about 20 genera of corals out of 70-some that survived, and they all died when things got good. In other words, the corals that made it through the Jurassic mass extinction were the small, slow-growing, but very tolerant. They could take it. And so they made it through, and most corals died. But almost all of those died when things got good. So when things are bad, they were doing okay compared to others. But when things got good, they didn't. Whereas corals now are doing much better because when you have the next big building of reefs, only about 55% or 45% died. Now, I'm saying corals are getting healthier. The Triassic corals didn't do so well. They were the first try for scleractinians. The next try, they're doing much better. These 26 genera can be found in Wells' list of species that made it through the Triassic, or the Cretaceous extinction. So these are called the Lazarus corals because they come back from the dead. These corals, 26 genera, made it through that big volcano and the bolide and the bad conditions in the Cretaceous, and they're still with us today, which means these 26 genera made it through the Cretaceous mass extinction. They made it through the Paleocene, Eocene thermal maximum. They made it through a big mortality of half the corals in the Caribbean in about 2 million years ago. And so they're still with us. And if they made it through all that, we're dishing it out faster than other things by burning all the coal and stuff like that. But I think they might make it again. They made it through all that before. But what's interesting is that fast-growing corals, these are all just like made it through the Triassic. I'm sorry, I'm really biased, aren't I? All of these made it through the Cretaceous extinction. The ones that made it through the Triassic were also mound-shaped, slow-growing time. For all the fast-growing times went extinct, and they had to start whole new ones again. And that's what happened this time. They went extinct, and all of these are fast-growing corals. Nothing was fast-growing made it, but they had to start all over with brand new kinds. And they're called Faustian corals because they can grow fast, they're glorious, they're beautiful, have an easy life, but in the end they have to pay the devil. So there's ways to be resilient, and we combine two things in coral reef science. They say we define resilience as the ability of reef to absorb recurrent disturbances. In other words, acclimate, adapt, tolerate, don't let it take you. Whereas ion rebuild, in other words, if you're knocked back, you can rebound by reproducing, successfully recruiting, and healing. Well, I think corals, the ones that make it through the mass extinctions and the ones that start over every time, not start over, just a new one starts, the massive ones adapt to survival is more selective than reproduction, or in other words, the absorb is more favored by selection than the recovered. Cropera, another fast branching corals, is the opposite. Fast growth is favored over survival. Now, this is a picture from a recent MEPS, and it's just an article where it showed corals that bleach, and those that are with them that did not bleach, after this effect, did not reproduce for 4 years because it was so expensive to recover if you bleached, or just withstand it if you didn't bleach. You don't reproduce for 4 years, but you survive. And this is generally the pattern in these mound corals. Bleaching, tissue damage can suspend, I'm terrible. Tissue damage can suspend gamete production for several years. Bleaching can prevent completion of gametogenic cycle the following year. Repair of damaged tissue costs energy otherwise allocated for gamete production. In other words, the ones that make it are selected to survive, and they survive, but they don't reproduce.